Introduction to velocity. What is it? How do we use it? Well, velocity is a lot like speed, but a little bit different. It's like speed, but new and improved. It's like speed, but it has one little extra piece of information to go along with it. It's speed and the direction. That's it. It's a speed and the direction. So you're probably used to seeing speed in miles per hour. That's what you see on your car when you go on the highway, or anywhere really you see miles per hour. But we don't use miles per hour because we are in a science class. So we use metric units. And metric units are meters per second. Because you remember the SI unit for distance is meter. The SI unit for time is second. Also written like this. Also meters per second. They describe the same thing, though, just with different units, like miles and kilometers, or like pounds and kilograms. 30 miles per hour is about 14 meters per second, just to give you some scale. And 60 miles per hour is about 27 meters per second. Just think of it like another wacky unit. Not like something, I don't know, confusing or like scary. If it confuses you when you're thinking of a concept, don't think of meters per second, just think of miles per hour. Anyway, velocity is speed in a direction. So this is a speed, 45 meters per second. To make it a velocity, I just add a direction, like 45 meters per second west. That's a velocity. 15 meters per second, that's a speed. A velocity version of this would be 15 meters per second backwards. Or maybe 60 meters per second versus 60 meters per second to the left. You see they're basically the same. 4 meters per second or 4 meters per second north. Any direction you add. It could be, you could say it's 15 miles per hour versus 15 miles per hour on the way to school. One's a speed, one's a velocity. So why reinvent speed? Well, the whole point of physics is to predict the future, one of the basic goals. And if we have all the information about the present, we want to be able to tell exactly what will happen in the future. We want the concepts we use, there we go, to be as informational as possible so that we can pack the most future-seeing ability into the smallest number of quantities. So this is a big boulder. It's going at 20 meters per second. It's going to crush you, or your worst enemy. You don't really know. Should you start running or laughing? You don't know, because you used speed instead of velocity, right? Speed does not help you predict the future as much as velocity does. So if instead of giving you the speed, I give you the velocity, and I say, well, this is going 20 meters per second to the left. Now you know to start running, right? Now you know to start sprinting. Velocity is more useful than speed. So you're going to go get crushed by a boulder, or hopefully escape, and your enemy's going to laugh at you. Unfortunately, but at least you know, right? But we can't just use the vague idea of velocity. This is a science class, so we need to calculate the velocity. And it's not very hard. It's basically the same thing as calculating speed. There's maybe one little quirk that I'll tell you about when we get there. The hardest part about calculating velocity is calculating the speed part of it, though, so I'll show you that. Let's think about it in terms of units you're familiar with before we go into the objective metric units. If you go 30 miles in 1 hour, how fast are you going? 30 miles per hour, right? Because you go 30 miles in 1 hour. So what if instead you go 30 miles in 2 hours? How fast were you going? Well, I mean, you go the same distance, but it takes you twice as long, right? So you're going slower. Specifically, you're going half as fast. So 15 miles per hour. This should make sense to you before you do any calculations. Notice, though, you could have done a calculation. The thing you did to get these numbers was an invisible, lightning-fast, subconscious calculation in your head. 30 miles per 1 hour. 30 over 1 is 30. For the second one, you go 30 miles in 2 hours, right? So you go 30 miles in 2 hours. 30 divided by 2 is 15, so 15 miles per hour. You make a fraction. And that's the same thing you do with velocity. Velocity is the change in position over the change in time, and then also a direction marker. This part is basically just the speed part. So, here's some examples. If I go 20 meters forward in 1 second, what is my velocity? Well, 20 meters over 1 second, because you have distance over the time, right? So distance over time, which is meters per seconds. So 20 meters per second, which is 20. 20 divided by 1 is 20. And then you also need the direction to make it a velocity. So the velocity is 20 meters per second forward. If you move 20 meters backwards in 2 seconds, what's your velocity? Well, two things are different here, right? It's 20 meters in 2 seconds, not 1. And also, you're going backwards instead of forwards. So your velocity is 10 meters per second, because 20 divided by 2 is 10, backwards, because that's your direction tag. Finally, if you move 20 meters forward in 3 seconds, what is your velocity? Well, you have the distance over the time, like the number of meters over the number of seconds. 20 divided by 3 is 6.67. So, this one you probably could not do in your head. But the answer is 6.67 meters per second forward. The unit is here, the magnitude is here, and the direction is here. But if you didn't remember those, that's okay, as long as you got this. It's not as important to know what every single part of it is called. It's still important, though. So, getting the change in position. Let's say that you don't get the distance and the time. You get something else. What they give you is the time and the velocity. Can you figure out how far you go? Well, let's think about it with units you're familiar with, because you'll probably be able to do it in your head. If you go 60 miles per hour forward for 1 hour, how far do you go? 60 miles per hour for 1 hour? Well, you go 60 miles, right? Let's say you go 60 miles per hour for 2 hours. How far do you go? Well, I mean 60 miles per hour. The first hour I go 60. The second I go 60 more. So I go 120 total. You probably didn't do a fraction in your head or any multiplication to get that. But notice here. What you did was you did 60 miles per hour for 1 hour. So you did the velocity times the time to give you your distance. And I'm going to do that right here. So, velocity equals change in position over change in time, and the direction marker. Can't forget about that. If you do some algebra, you can get this alone. Now, to get rid of a divided by change in time, you can multiply by this whole thing. When you multiply it, it moves up here, next to the velocity. So, the velocity times the change in time is equal to the change in position. So I figured it out. You can also figure this out with dimensional analysis if you want, not that you have to, but you know velocity is in meters per second, and then the change in time, well, that's a second, right? So this cancels with this, and what it gives you is meters. So if you want to get meters, you do meters per second times seconds. But remember it whichever way works best for you, rearranging the formula or dimensional analysis. So some examples. If I go 50 meters per second forward for 2 seconds, how far do I go? Use the formula, right? 50 is the velocity. Well, 50 meters per second forward is the velocity for 2 seconds. So I go 100 meters. If I go 20 meters per second backwards for 1.5 seconds, how far do I go? Well, this is the magnitude of the velocity. That is the magnitude of the time. So I go 30 meters backwards, because I'm going backwards, right? And the change in position will normally have a direction too, because you move in some particular direction. So if you go 2 meters per second to the left for 3 seconds, how far do you go? Well, 2 times 3 is going to give you 6, right? You go 6 meters to the left. That's where you end up. Hopefully this makes sense. So what happens if instead of wanting to get the position here, you want to get the time? Well, this is the formula. Velocity is the change in position over the change in time plus your direction marker, which you can't forget. And you got to do some algebra. I'll do the algebra for you next slide, though. So you can do this in your head with things you are familiar with, probably, which is, miles per hour. So let's say you go 60 miles per hour. How long does it take to go 60 miles? It goes an hour, right? Because 60 miles per hour. So 60 miles per hour, same speed. How long does it take you to go 30 miles? Well, it only takes you half of the time to get halfway there, right? So it will take you half an hour to get there. Let's rearrange the velocity formula to find something that makes sense with this. Velocity is the change in position over the change in time and the direction marker. Don't forget about it. So doing some algebra, if you want to get change in time alone, you want to isolate it, you act like it's a variable on the bottom of a fraction. So you have like x equals y over z. And you remember what to do is you can just take this and flip them. Just make them switch places. So if you have x equals y over z, you can turn that into z equals y over x. So what you would get is the change in time equals the change in position over the velocity. Because this and this just switch places. If you prefer, you can also remember this with dimensional analysis. Change in position is in meters, right? And the velocity is in meters per second. So you have meters divided by meters per second. Maybe you don't remember, but when you divide by a fraction, you multiply by the inverse, right? So you have meters times seconds over meters, and the meters cancel, and you only get seconds. This works out dimensional analysis-wise too, but do whatever you want to do to remember. Here's the formula up here. So if I'm moving 50 meters per second forward and I've gone 100 meters, how long did it take me? Well, change in position, the velocity. 100 divided by 50 is 2. There we go, 2 seconds. If I'm moving 20 meters per second forward and I have gone 60 meters, how long did it take me? Well, first second I go 20, second I go 40, third I go 60. But for numbers that you can't do in your head, you're going to have to know this. You take the change in position, right here, 60 meters, over the velocity, which is 20. 60 divided by 20 is 3, so it would take you 3 seconds. Finally, if you are moving at 2 meters per second forward and you have gone 1 meter, how long did it take? Well, you go 2 meters per second, right? And it only took you, or you only went 1 meter. So it took you 1/2 of 1 second. If you could do this all in your head, great. You will get numbers that you can't do in your head. So this formula is something you should know how to find. Almost done. There's one more thing you should know about velocity. And it makes it easier to use once you get it, but sometimes it makes it harder for people to get it. The biggest annoyance when I'm dealing with this is that I have to say or write the direction every time. I have to say in front, or forward, or backwards, or to the left, or to the right, or east, or northwest, whatever. What would be really nice is a way to shortcut writing all these words, so I don't have to write out northwest, which look at how long this takes me. Northwest. That is a pain, and I want to write that down 6 times when I'm doing a problem. There's an easier way. We could use a symbol, maybe. We could use the symbol to tell us the direction that we're talking about, so that I don't have to write down the whole word. Kind of like you write LOL, right? Instead of laughing out loud. Even though nobody says that, but whatever. It's a shortcut. 2 meters per second forward could be something like this, with a dot. Backwards could be an empty circle, right? So a full circle is forward, an empty circle is backward. Or I could do what? The east could be this little euro sign, right? 2 meters per second east. That's faster than writing E-A-S-T. West could be like a smiley face. Whatever you want. Doesn't matter. It's a symbol. It doesn't have to make sense. Like the symbol for radioactive things is like this, right? And this doesn't look anything at all like a radioactive thing. Like radioactive atoms don't look like this. It's just a symbol. Anyway, we do use a symbol, but it's none of these. We only use two symbols most of the time. We use a plus sign and a minus sign. Now, people will be confused because these are things that you use in math. And we use them here because they're kind of related to math, but not in a way you need to know right now. Just think of them the same way you would think of a smiley face, or a hollow dot, or a euro sign. They're just symbols. And sometimes we use arrows, but we'll do that later. So, we only care about motion on one line for this particular video, one-dimensional motion. So for every problem that only involves one line, we only need two directions, right? We got this way and that way. And we'll assign one of the directions a positive sign and one of the directions a negative sign. For this kind of line, we have this way and that way. We're going to assign one of them a positive, one of them a negative. If I wanted to, I could also take this line, any slanted line, and basically it only has two directions, right? Only those two directions are part of the line. This right here, if I want to do this, that direction is not part of the line, because if I move that way, it takes me off. We only do motion on which I stay on the line. So, we have a plus and a minus sign for every line, right? But if I just tell you that you should go plus 2 meters, you're not going to know what that means. If I tell you that you're on a football field going minus, 4 meters per second, you're not going to know which direction that is unless we already have established previously what sign means what direction. So we do that. Basically, you can have lines or where there's a forward and a backward, right? Forward, north-south. This is the compass, in case you don't know. What is the mnemonic? Never eat soggy waffles. That's one that people use sometimes. I remember north and south is really easy. And then the word we is what it has over here. So any way you want to remember that is okay. Anyway, east and west, that's another line we can have. We can have right and left. We can have up and down. You're going to assign a particular symbol to these directions on any line. Forward is going to be positive. Backward is going to be negative. North is going to be positive. South is going to be negative. East is going to be positive. West is going to be negative. Right is going to be positive. Left is going to be negative. Up is positive. Down is negative. You just have to memorize these, but it's not too hard because it's mostly intuitive. The only really weird ones are these. And it makes sense because this is positive and this is positive. So it's like up and right on the compass. So let's see you try to do it. 45 meters per second forward. What is the symbolic version of this vector? You would say positive 45 meters per second. This means forward. So 50 meters per second backwards. What is that symbol? Negative sign, because backwards. Negative 15 meters per second. What about this? 60 meters per second to the left. Is the left positive or negative? Well, I'm symbolically going to say negative 60 meters per second. North. What is north? Positive. And then west. In case you forget, it can help to draw the compass sometimes. And then never eat soggy waffles. Or you could remember north, south. That's easy. And then we. That's what I did. Anyway, west. This way is west, right? It's on the left of the compass, so I'm going to give it a negative. Call it negative 6.2 meters per second. You can also do this to tell you the direction of locations. So for example, if I say that something's 4 meters in front of me, I would say it's at positive 4 meters. But if it is 15 meters behind me, I would say it's at negative 15 meters. 60 meters to the left of me, well, I would say that that's negative 60 meters. 4 meters north is going to be positive 4 meters. And then 6.2 meters west is going to be negative 6.2 meters. That's it. You might say, wait a minute. In front, behind, to the left, that's not a line. But crucially, whenever I say this, whenever I say a sentence, there are only going to be two possible places a thing could be. If I have this, then it could either be in front or behind. So these go together. But for this class, you will never have to deal with behind and to the left. Nope. Not going to be a problem. Because this is me, this is behind me, this is to the left of me. These are not on one line with me. So that's not one-dimensional motion, and that's a problem we deal with later. Similarly, north and west, right? You might say, well, wait a minute. If I see positive in a problem, how do I know if it's north or if it's east? And the answer is, we will tell you that you're either dealing with a north-south line or an east-west line, never both. So hopefully that was helpful.